We're going to review the AP method for justifying absolute extrema, which means the absolute maximums or absolute minimums. I realize that the resolution on this is not so hot, but this is your homework worksheet for today. The solutions are also attached on the document that you have access to. So even if this stuff's a little blurry, that's okay. You can see it much more clearly if you go to the actual document link. What you care about in this video is the process. So what I have here is a pretty curvy function over a restricted domain, and I want to find out what is the absolute maximum value. All right, so in other words, what's the highest y value that this equation will ever achieve over that interval? So I'm going to assume you're up to date on the curve sketching part. You would build your number line, first derivative number line, using critical values and endpoints. But what the purpose of this video is to remind you what the CCCC stands for from the AP's justification point of view. The first C stands for candidates. So after I've filled out my number line, if I wanted to find out where could the absolute maximum value be, it could be at -1 because according to my number line, my function starts out, it goes uphill for a while because the first derivative is positive, then it goes downhill for a while, then it goes uphill for a while. So x equals -1 is a candidate to be the highest spot on the graph. So that's why that's there. Now these two are both there because the AP wants you to include the endpoints. Whether or not the endpoints are going to be a maximum or minimum, they don't care. They want you to include them, so always include the endpoints. So we have now done the first C, the candidates. The next two C's are compute and compare. All right, so by compute, what that means is take each candidate, plug it into the original equation so you can get out a y value. That's what I've done there. A lot of mental arithmetic. And after I compute, I should be mentally comparing, or even on paper, comparing these values. So I have the candidates, I've computed their values, and then I'm comparing these values to see which one is the greatest. My final step would be to conclude. Since I'm looking for the absolute maximum value, I see that this 8 1/3, which occurs at x equals 4, ends up being the maximum value. By the way, sometimes I'll do this in my solutions, sometimes not. A really nifty way to do your compute and compare is to put the values into a t-chart, because that's kind of what your brain's doing anyway. A couple other points. I didn't have a justification here, but that's because it was written up there. If your justification is not in a nearby section of your work, then you should include it in the candidates part. Let's move on to the second problem, which is a little bit clunkier on purpose. It says, hey, use the CCCC method to find the location of the absolute minimum value. Okay, so if I'm going for the location, I'm not going for the y value like I was in the previous problem. In this previous problem, the absolute maximum value is the y value. It just happened to be located at x equals 4. In this problem, we're only after the location. Well, they gave us a graph of a derivative. So from this, I can make a number line. Hey, my derivative is in positive territory. My derivative is in negative territory. My derivative is in positive territory. Remember, when you make that little number line, now you have an idea for yourself. Function going uphill, downhill, uphill. My candidates would be E because it's a minimum, A and G because they're endpoints. Now the compute and compare in this case is going to be pretty rough because you don't have an equation to work with. And this would be a clever AP trick just to see how flexible you are with your calculus thinking. So let's say I'm going to compare E to A. Well, according to this derivative graph, or this, my function spends a significant portion of time going uphill because the derivative is positive, and significantly uphill, and then a tinier bit of time and a tinier amount of downhill. So f of E, or E's y value, is definitely bigger than A's y value because the integral of that derivative from E to A, or from A to E, is positive. That's deep thinking, so I know that's a rough one. And now let's think about this. As we go from G to E, the derivative is positive that whole time, so G must be at a higher y value than E because the slope during that span is positive. So G is bigger than E. Yikes, but let's think about what's happening here. Here we know that E is smaller than G. Wait, let me think. Now I gotta think, darn it. Okay, I think this is how I would think of it. E is bigger than A, but G is bigger than E. So that leaves A to be the smallest y value of these three. So A is the location of the absolute minimum value. We just don't have enough information to calculate a specific y value. Okay, so you can see that these problems can be straightforward and arithmetic, or deeper with deeper thinking. But the bottom line is, anytime you're looking at a absolute maximum or minimum value on an AP test, you need to justify using the CCCC method in some way, shape, or form. The problem on the back is a previous AP free response question, so it's really good practice to see how they might imagine the CCCC shows up.